So with that single point calculation done, now we are going to jump to our next type of calculation, which is our Porbey diagram calculation. I like to call the Porbey diagrams that we generate in the OLI software real solution stability diagrams. And why do I like to call them real solution stability diagrams? Because we, in our calculations, we actually incorporate the activity coefficients of the species that are part of the system. So when Porbey created his atlas, you will go back, and if you're a metallurgist, you will know that if you go there, it's all in pure water, right? Everything is done in pure water. And that's a good approximation, but in reality, we don't have pure water. We have ions dissolved in our water, and the ions or the salts make this water or these solutions non-ideal. So then you have to incorporate this correction, which is the activity coefficient of the species. And we do that. We do just that. The software does those calculations for us. And it doesn't matter. It doesn't matter if you're using the AQ framework, the MSE framework, the MSE SRK framework. We can calculate those Porbey diagrams. And you also, another benefit is that not only you can include those activity coefficients in the calculations, but you also can include the effect or see the effect of temperature, pressure, and concentration of species in your Porbey diagrams. And we will do examples showing that, right? Another thing that you can do is that in some cases, when you're doing pH, so when you're doing your Porbey diagram, you have here your pH. And in the experiments, sometimes you cannot use chlorhydric acid as your acid for titrating or reducing the pH. You need to use sulfuric acid or nitric acid or any other acid. The software also allows you to do that. Okay, because if you were using chlorhydric acid can create complexes, and it can create a lot of issues in the laboratory. So you can use some other realistically modeled acids and bases to vary the solution pH and match what you see in the Porbey and what you see in the experiments. This is really quickly a revision or like a summary of what a Porbey diagram is. So a Porbey diagram will give you, it's a plot that will give you a map of potential versus pH. Okay, so that is what is going to basically be showing you. And this is going to show you different regions that from the metallurgical point of view or corrosion point of view is useful to identify if you will have corrosion areas, if you will have what we call a passivity area where corrosion still happens but at a lower rate, and the immunity area where corrosion is not supposed to happen. Everything remains untouched, everything remains as an elemental, in this case copper, and there is no corrosion or dissolution of any metal happening. This is a thermodynamic plot. It's all based on thermodynamics, and we do not provide information of reaction rates or kinetics effects. Okay, so this is again purely thermodynamics, and what you will see is the equilibrium lines between one species and the other one. Okay, So, for example, in this case, this line, so you will see there are vertical lines, there are horizontal lines, and there are slope lines, like the ones with this slope here, slope lines. So if you have a vertical line, it means that you have a chemical reaction. You are not transferring any electrons in any way, okay? The reactions are not being affected by the electrode potential. So no matter how much you increase the potential of this system, the reaction is the same. And the reaction is basically is going to change if it happens at a specific pH. Or this reaction is going to occur if it happens at a specific set pH. So this is a chemical reaction of copper plus 2 going to copper oxide. And notice that because it is a chemical reaction and it's not an electrochemical reaction, the oxidation state remains the same. So it's plus 2, plus 2. Okay. Now there is another type of reaction that is represented by this vertical, this horizontal line, this one here. This is my horizontal line. When you see horizontal lines, that means that it's a electrochemical reaction and that you are involving electrons in this reaction. So in this case, for example, what you are doing is that you are passing copper, elemental copper, to copper plus 2 here. You are corroding the system. You are creating electrons, or electrons are being pushed out of this copper here. And also notice that this is a reaction that is a function of pH. So you change. Sorry, that is not it's not a function. The electropotential in this case is the potential here remains. It happens a specific potential because it requires electrons, but it's not a function of the pH. Okay. So that is what's happening here. This is a trouble area where we are having electrochemical reactions because we are corroding the system. Now, the last line that you will see is the one that is here, the slope line, okay? And that means that these reactions are both a function of potential and a function of pH. Okay, so you will have that that dependency, potential and pH are both driving this type of reaction. So when we identified all the species and all the equilibrium lines, which ones are chemical reactions, which ones are electrochemical reactions, etc., then we start finding regions. And like I was saying before, there are different regions. This gray region represents the immune to corrosion region. We want to be here, like if you were doing a cathodic protection, for example, you want to reduce the potential in such a way that you want to be here in the immunity region. The green color represents the passivity region, where the passive film is formed. And again, corrosion happens, but it's going to be delayed. It's going to be happening, but at a lower rate, orders of magnitude, much less than an active corrosion. And this yellow line, yellow region here will represent the corrosion region. Okay. Now, it is also important to highlight that wherever corrosion happens, or at least the one that we study happens in aqueous systems. So we want anything that happens in this water stability region is the corrosion that we want to study or understand, like what's happening within this water region. So you will see that there is this orange line here. That's the water oxidation line. That represents the oxidation of the water oxidation reaction. If you increase the potential above this line, Then you will start seeing oxygen being formed. Then you will see another line here is the reduction, the water reduction line. If you decrease the potential, then you will start seeing bubbles, but they are this time being mostly due to the formation of hydrogen. These are the cathodic reaction. This is the cathodic reaction that is happening on the surface. Okay, so again, anything that we want from a corrosion point of view will be within this water region. Okay, so this is exactly how we do it in the software. The same coloring, the same, we put the water oxidation lines, the water reduction lines. All of this is how we plot it in the software. So the first example that I want to do to show you how to create these Pore diagrams is the stability diagram of iron in a water system. We could add sodium chloride if we want to make it a little bit non-ideal, but it's up to you if you want to do that. Let's go to the software. Are there any questions of how to interpret those diagrams?
I have a question, Diana.
Sure.
In this diagram, I can understand what affects the pH, but what is affecting the corrosion potential? Is that the oxygen amount, or what other input affecting the potential? What condition change the potential, basically?
The effect of the corrosion, but what was the question again? I didn't quite get the second part.
The y-axis, like
Okay.
what condition change this potential? Like
what condition? So okay, so there are several ways that you can, yeah, the pH, like you add as acid, you add a base, you add whatever, right? For the potential, and this is for a specific electrode reaction. So this is not for a system, for a complete system, but it's okay. So there are, how do you change this potential? So in the lab, you can use what we call a potentiostat. And literally what it does is just puts up and down these potentials. You say, I want my system to be at this potential, and it just applies some current, and it makes sure that you are in this potential. That's one. That's in the lab.
Mm-hmm.
In the real life, there is something is called impressed current. This is for pipelines to cathodically protect them. So they also pass a huge current, and that is going to make the potential lower. That's another one. Another one is a sacrificial anode. So in corrosion or in electrochemistry, if you have an anodic reaction, you need a cathodic reaction. So a sacrificial anode is like a big bar, let's say maybe it's, it could be made out of zinc. That's what in boats, they also put like these little big, or these big pieces of zinc. They corrode, and that corrosion sends electricity or electrons to the cathode, and it reduces that potential as well. And there is a fourth way of doing it, and is adding oxidizing or reducing agents in solution. So you can add, what is an example? There is chloride, I don't remember. There are some salts that have some chloride components, hypochlorite, I think, and you add them into the water, and that will reduce or increase the potential of the solution, and that will also have an impact on the potential of the metal. So there are different ways. It's not like straightforward like the pH, but that's how you change that potential.
Mm-hmm. So in our calculation, or in our thermodynamic stable state, it's going to be a function of the solution chemistry and the contact metal. Is that I understand
it? It will be in our, no, we will directly change this.
Okay.
In our calculations, we will, it doesn't have to do anything with the It doesn't have to do anything with the bulk solution or what you add or anything like that. We calculate that separately for the bulk solution, but for like when we are doing these calculations, we just simply do a sweep.
I see. So it's additional input. It's
Yeah,
not.
it's just exactly. Yeah, we are just this is a variable that we just sweep.
Okay, I see.
2 to 2, and that's
Yeah.
it. But in
Yeah.
real life, it's not as simple as doing a sweep. You need a machine, a potentiostat. You need some other things to make these changes. Always, mostly, all of the time, impressing current to the system. But in a simulation, from a simulation point of view, this is just a sweep.
I see.
Yeah. And when we go back here, I'll show you where you just say the range of potential is from here to here, and that's it. That's all we do.
Thank you, Dan.
Okay, no problem. Okay, so let's do our first example. It's going to be simple. What is it? Here. Our first example is going to be the stability diagram of iron in water. And we will see how to create this. Okay, so let's go back to the software. We're going to add a new stream. Now, this is a good example. In here, you'll see that if I want to add a new stream, right? I don't see any actions in my actions pane. Where did they go? I don't know. Well, the reason is because you are at the subcalculation level. And when you're in the subcalculation level, there is nothing else you can do after that. So there will not be actions here. You need to make sure that you're clicking on the stream or that you're clicking at the global stream. The global stream will show you everything. The stream level will show you only the things that you can do within a stream. But we need to create a new stream. So we are going to call this iron Pore diagram. Okay. And this iron Pore diagram, again, we could add sodium chloride here, or we can just put water. But because we can calculate the activity coefficients of my water, so I can add some sodium chloride too and see what is the impact on my Pore diagram. Okay. Now, again, we are doing everything. The MSC is the default framework for our software in this version. We are going to leave temperature and pressure 25 degrees C, everything the same. Okay, that's my water. This is my bulk chemistry. That's it. I don't need to specify absolutely anything else. My framework, the phases, everything is by default. But I go to the Add Calculation button. And in here, you'll see that I have the stability diagram option. If you click on that stability diagram option, now it will take you to a different type of view compared to what we saw for the single point. This view will add two more different sections. The first section is the calculation parameters. This section is asking you which titrants do you want to use to vary the pH of your system. So we want to go from 0 to 14. In some cases, people want to go even negative values up to 16 pH because they are working with sodium hydroxide type of systems that are very high in pH. And you can select. You can select chlorhydric acid as the one that you use for your Pore diagram, for the acid pH values, and sodium hydroxide. Now, if you are not happy with those titrants, let's say you are like, no, we don't use chlorhydric acid in the lab because it creates a bunch of complexes, etc. So we want sulfuric acid. So you simply add it here under the inflows. You put the sulfuric acid and you select the sulfuric acid from your list of titrants. but you gotta put it under the inflows or else it will not show. So if I didn't put it, and if I had my chlorhydric acid, or now I don't have my chlorhydric acid, let's say we had the chlorhydric acid, right? And I want the sulfuric acid, it's not there because I did not define it in my inflows. So I have to define it in my inflows in order to be able to select it. Same for the titrant. If you want to use another titrant, lime, any other thing that is basic, you can do the same. The contact surface. Contact surface is nothing else but the element, the material that you want to study. In this case will be iron. You can add any other element, truly. Like you could add alloys that we have in our data bank. You'll see here there are some 2205, 304s, 316s, or you start seeing all the periodic table available here. Copper, indium, molybdenum, isomonel 400, nitrogen, radium, any other element that is available here, you can put it in as a contact surface. I want to put iron +2, or iron, sorry, the elemental iron. That's it. I could have typed it. I could have looked for it. Okay. And the software will also add it as an inflow. You don't worry about that. The software will do that for you. Second thing, the software has also turned on by default, after you selected your contact surface, the redox button. So it has selected iron and sulfur. Both of them are turned on by default. Now you define, do you want the sulfur on by default or you want only the iron by default? I will go with the default at the moment. And then you start playing with the what if scenarios. Okay. And I don't know why it turned on. Actually, I don't know why. So maybe because the sulfuric acid is there. Actually, I'm not going to turn on the sulfur. If you have the sulfur, just remove it. I don't know why, actually. Shouldn't be selected. Going to read. Yes, only the iron. Okay. Now in here to the right, the software also says, okay, you have acid, you have a base. This is the range in potential. This is what we were talking about. Goes from -2 to 2. The range in pH from 0 to 14. And some other things. Where do we change this if we don't want these ranges by default? We go to the specs button. And that will open a new window where there are a bunch of things here that I personally like to change. Like, for example, I like to change that the software shows me the oxidation reduction potential. So I click on that. Okay. Under the axis, these are the defaults. pH range 0 to 14. Y-axis -2 to 2. You could change this -1 to 1, -3 to 3, any other value you want. Metal activity. The metal activity by default that we use for any ion in solution is 10 to the -6, a very small value. But if you go to the atlas of Torbay, you'll see that he will have like different lines for different activities. So you will change just those equilibrium lines by changing this activity. But every single one of those lines is calculated using the Nernst equation. And again, the activities of this species down here are assumed to be 10 to the -6. Okay? So click OK. It will take the changes that you made. And then we can go ahead and calculate. Okay, calculation completed. the stability diagram is how we call our results in this specific calculation. To see the results, we go to the stability diagram. Good. Save. If anything happens here. So again, gray region, immunity, iron, elemental iron. Corrosion region, here it is. We added sodium chloride, so you will see some chloride in here. The green region represents the formation of a layer. In this case, the layer is hematite. It's mostly that layer that is red that you see on the bridges or in the gates, you know, like they start like orangey type of reddish type of oxidation or corrosion rates, not corrosion rates, but like color when you see them. That is the result of this hematite. And down here, you will see another section of a solid phase, which is the magnetite phase, iron 304. This one is the one that we want. This is actually a protective layer, very good protective layer that we want in our system. You also see the lines here for the water, water reduction line and the water oxidation line. This would be the stability of water. You have a natural pH. What do we mean by natural pH? Is the pH of the bulk solution. It's more or less 7. And we also put in the map where the oxidation reduction potential of the bulk solution lays on this plot. So it's saying that at these conditions, 25 degrees C, 1 atmosphere, iron in sodium chloride solution will form this layer of a hematite on the surface. That is what is telling me here. At this pH and at this potential. That's what it's telling me. Any questions about how to interpret this plot or what it's telling me? Mariana, Joaquin, I know that you had questions about the stability diagram or the Porbey diagram. Okay. Let me see what else I'm missing here. Okay. So
it is okay. Thank you. Yeah.
Okay, so sure, no problem. So that's the stability diagram. Now, again, if we go back to the definition, or maybe even better, right-click, copy this stability diagram, and paste it under the iron Porbey diagram. Paste. And I'm going to start adding some other components, like H2S. Again, the H2S is always a problem. So we go back to the stability diagram. And we say, you know what, in our inflows, we also have H2S, hydrogen sulfide, a very small amount, 0.1. Everything remains same. My titrines, my chlorhydric acid, and my contact surface. Okay, so I have all of these. The only thing I change is here the hydrogen sulfide. Another thing is, okay, we are going to include the sulfur oxidation state as well. Let's see what species we form if we include or if we let the hydrogen sulfide to react or to change oxidation stages. So click on the sulfur, right? So redox selected, triple check that you have sulfur and iron. Okay, in my system, selected, and then click calculate. We're going to see if there are some differences in the Porbey diagrams. Okay. Going to save and go to stability diagram. Okay, I do see differences here. So you can just compare, visually compare. Now we are having an extra region down here where we were supposed to have corrosion. We are actually forming another layer, an iron sulfide here. And actually, our system, you see the natural pH and the oxidation reduction reaction is right on that layer. So in theory, what this is telling me is that this system, the iron sulfide at that composition, at that concentration, is creating a protective layer and is delaying corrosion. Okay, that is what it's telling me here. There is another layer here, iron sulfide here, but that one is below the reduction line, so probably it is not likely to happen. I mean, because it's not within the.
Diana,
Yes.
could I ask you something? Because I'm having some problems in the part of definition.
Okay.
In the inflows, the units, it appears as mole per hours, not only as mole. I don't know.
Okay, so what we can do is click on the stream level here, the iron carbide diagram, and make sure just go here to your units manager. And we haven't gone through the units manager yet, so we will learn.
Sorry for interrupt.
Go
First, when I copy and then paste calculation, the system changes by default from batch to flowing. I don't know why.
Okay, so let's even do it. Let's change that. So now let's go to the streams level, all the way to the global stream.
Yeah.
Then you're going to go to tools. Then you go to units manager. I think it's like that. Let me see. No. 1 second. Tools, options. What did my... It's not responding. I gave it too many orders. So you should say, okay, tools, options, units. Yeah, it's the same. And then for the stream, make sure that it goes metric, batch, moles.
Yes, I have it like that.
You have it already like that?
Yeah.
Yes, but when we thought of, for example, your stability diagram for one, you copy and paste. The second stability diagram calculation changes from batch to flowing.
That is very weird. What could it be? So streams, let me see again. Units manager. We are working with a stream. It should be by default batch. And you are having it as batch.
Yes, when we add a new stream, it is always in batch.
But when you copy it, it changes it to flowing. Interesting. Okay, let me do one thing. In my case, I don't know if that happened. So moles, paste. Which version of the software are you using again? The 11.5?
Yes.
11.5. Okay. I don't know. I would need to see that file and see why it's changing from batch to flowing. But for now, I guess my only suggestion is click on the stability diagram or on the stream level and go to units manager and change, well, actually no, it would be at the stream
generally what I do is just to copy the parameters and then
another way is moles. Like if you click on the hyperlink, just change from flow into batch, and that's it. That will be the fastest. There are many ways. Is it possible, Joaquin, you save that file and send it to me through the portal and I'll take a look?
Yeah, for sure.
okay.
Sorry about that.
Thank you.
No, thank you. Okay. I forgot where I was. I think it was here in the stability here. Okay, so again, now you're having these pore-based diagrams, and it will give you a lot of good information from a thermodynamic point of view of what's happening to the protective layer, right? Because at the end of the day, if you are seeing it from a corrosion point of view, you want to have a protective layer, you want to minimize corrosion, etc. So at the beginning, I said, okay, yeah, you can study components, activities, etc. What happens if we increase the ppms or the moles of this H2S? What if we just increase it by 10 times, right? And then you start seeing the effect of the concentration of those species on the formation of passive layers. And again, like I showed in this isothermal calculation, you can replicate these same conditions and go and see how much of the actual layer is being formed, right? In moles or in grams or etc. And in here, I actually didn't see I don't remember. No, I don't think there were very many changes by increasing the H2S. So you start saying, okay, but we are at reservoir conditions. Temperature and pressures increase. They will have an effect on the movement of those layers. Probably you have a question.
Hey, Dan, I have a question here, Diana. So I see the passive film that forms this iron sulfide FES.
Mm-hmm. FES2.
If you see on the right side, there is another film, I think ferrous oxide, dioxide.
Ferrous
oxide, right? So my question here is, what kind of a species we call a passive films? Is that always a solid, or it could be an aqueous inorganic species?
Yes, it would be mostly a solid type of passive. That's a layer that is kind of solid, gelish type of. It's not an aqueous phase, no. I could have, and it's easier if I just remove the aqueous lines. If I go to my specs, I will remove my aqueous lines so I can just leave the solids. But yes, the short answer is yes. It's anything that is a solid phase, which not always, but generally protects the surface and decreases the corrosion rate. And it's a very tiny, when you go to the lab and you go and do an analysis in XPS or not XPS, I forgot, SEM, and you'll see that it's a nanometer layer. It's tiny, 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 and it has a huge impact on protecting the metallic surface against corrosion. And yeah, you will see a solid layer protecting the metal surface. The other lines that I was showing, they were just aqueous species that happen to be stable in the aqueous phase. But what we are interested here is in the solid phase. Corrosion, on the other hand, you don't want the metallic iron or the element to be in the aqueous phase, in the ionic phase, because that means that then you are corroding it. You want it either in an oxide or a sulfide or a carbonate or in the elemental state. So you don't want it in the ionic state. You don't want it in the form of a cation, because that is corroding it. Hope that answered your question.
Yeah, that's fine. Yeah, that's good. Yeah.
Okay. I just realized that I did not give you a break of 6 minutes, so maybe we can just go for a break and be back in 12 minutes after the hour for the last part of the training, and then that will be it for today. Okay, see you at 11 and my 11:12.
Yes, here we are.
Okay. I was going to write. Okay. Any questions at the moment regarding the 4-bay, except the units that we don't know what's going on?
I have a question.
Sure.
About the titrants in this diagram.
Okay.
I have always used the chlorhydric acid as titrant, the titrant by default, but there is a recommendation of using H2SO4, or it is independent to use chlorhydric or sulfuric acid.
It is well, it depends. So I've had laboratories where they do not want to see any chloride complexation, specifically at low pH values, like around here minus, like around 0 to 2 pH. And that is like complication in the lab where they have like the chloride contamination, cross contamination. So the reason why I use sulfuric acid is to show to avoid that complex formation. Like you see, there are some complexation here because we have sodium chloride in the system. What you do is to use sulfuric acid, but it will not have an impact on the end result regarding the other equilibrium lines. It's only for the formation of these complexes, because you're adding chlorides to the system, so you will be having complexation with chlorides. But for you, if you're working, probably you're working with corrosion rates, you are from a metallurgist point of view, these pH values here are not relevant, right? So nor the complexes, because you always want to operate between maybe above a 4, 5, 6 pH, where the carbon steel is more corrosion resistant, let's call it. Because if you're operating at these pH values, carbon steel is just useless, right? But no, I don't think that makes any difference. It's just from a research point of view where they don't want to see those complexes and they just don't want to form them, so they go with other titrants. But the end result would be the same.
All right.
If we put chlorhydric acid here. Let me see, in my inflows, I should virtually see the same plot, just that, I would be seeing the same plot because we do have sodium chloride in the system. It's just to manage to control the pH, basically. But it shouldn't have any effects. Okay, it's taken. You see, now I have even more. This complex here is a little bit more wider, the stability of that complex, and this is what people don't want to see in the lab. Again, in the lab. But from a applications point of view, we're having the exact same results regarding the formation of iron sulfide layer and the hematite layer, the corrosion region, etc.
All right.
That's it. Mm-hmm.
Thank you.
My pleasure. So let's save one last thing I want to talk about the pore bay diagram before we actually start calculating corrosion rates is in some cases you don't want to create a pore bay diagram that is only for one element. Okay, you want to probably see, because you have alloys, and alloys are mixtures of different elements. So if you have a stainless steel, you will have iron and chromium and molybdenum in some cases, right? Or nickel or some other alloying elements that are the reason why they are added to the system is because they increase the corrosion rate resistance. So far what I have shown you is, okay, this is a pore bay diagram with one element and this is how it behaves. But what happens if we now add chromium to the system? Okay, so if we go back to the iron pore bay diagram, or maybe we can just add a new stream. Let's add a new stream. And let's create iron, or let's put alloys. Alloy pore bay diagrams. I can show you the different options here. So again, we have probably water. I'm not going to put sodium chloride, nothing like that. It's just water, my water system. And I'm going to add a stability diagram. This stability diagram here, again, by default, we're going to leave everything by default. So we are going to say, okay, I want to see iron as my main contact surface, but I also want to see nickel, or no, let's put chromium. Chromium is a good one. And so we can add two different elements here, okay? So the software now is I'm going to click on the specs. So it's going to have two subsystems, okay? I'm going to say non-aqueous lines. I'm going to show the ORP. I'm going to leave my axis the same. So again, no aqueous lines and show ORP. Okay, and I'm going to calculate. Because if I don't do that, then it will be a lot of data. So we go to the stability diagram, right? Now what the system or what the software is doing here is superimposing two different pore bay diagrams in one. And it's easy for you or for the person that is designing an alloy or doing a specific, trying to understand why they are having protection or why they are seeing a lower corrosion rate or more corrosion rates or higher corrosion rates is in here is because you start seeing the effect of those two different alloying elements. So the software, however, you'll see that the iron is in red, everything that is in red, the red lines, the red colors, and the chromium is the bluish, turquoise type of color. The software highlights one or the other one, but not both at the same time. So if you want to see, in this case, it's highlighting iron, the iron system, but you can customize this and say, you know what? Okay, you show me the iron system. I am in the iron oxide here, the hematite layer. But what if now I want to see my, click on customize, that will open a new window. And then you select the shade subsystem would be the chromium. You click OK. And now it changes to how the chromium would look, right? So again, you'll see now that what the chromium is doing is even below the water reduction line, you're having protection against corrosion due to the formation of this chromium hydroxide solid layer on the surface. Okay, so that's the reason why you see how by adding chromium to the system, you are widening the area, the protective region of this alloy, let's call it 50% chromium, 50% iron, and it's going to be even at wider pH values and at wider potential values, it will be more corrosion resistant. okay? So you can do it with up to 3, 4. I think that I'm not sure if there is a limit on the amount of the elements here, but you can add as many as you want. You can add, in this case, iron, chromium, nickel, and do the same type of a study, but it becomes a little bit overwhelming to study so many systems at a time. So I wouldn't recommend putting more than 3 or 4 in one's calculation. But again, you go to the customize, and then you can highlight the nickel and see how it just, wow, look at this. So even a higher, by adding nickel, right? Adding nickel, so you're at a higher pH, at a higher potential, and even higher pH values. You're forming these solid phases that could potentially protect your alloy. Okay, so that's how you would do it for alloys. That's one way. The other way is, I like to show it because I get asked that question a lot, is, okay, so I have an alloy and I have the composition of the alloy is 50% iron, 25% chromium, 25% nickel. How can I create that alloy in the system? And again, this is specific to the pore bay diagram. This has nothing to do with corrosion rates. This is specific for the pore bay diagram. So where you go is a place that is called the Alloy Manager. So you go to Tools, and then in Tools, in the menu bar, you'll see an option that is called Alloy Manager. In here, you create your alloy. So in here, you'll say, I want to create a new alloy. However, you're limited to these families here. So we have copper nickel alloys, iron, carbon, manganese. We have the iron, chromium, nickel, molybdenum, carbon, ferritic, austenitic, the FCC, the face center cubic, the body center cubic. All of these are families. So you're limited to these families. So if you were to do a copper nickel family, you name it my alloy. Okay, you click OK, and then you give the composition is 60% and copper and 40% nickel. Either you define it in basis mass or mole, depend how you have it. In this case, we're defining it as a weight percent. Then we click OK. So this has created an alloy in my alloy database. Click on this alloy pore bay diagram again, and we are going to add a new pore bay diagram or a new stability diagram. Add calculation, stability diagram. And we are going to rename it my alloy, right? So we are going to leave water, everything by default, etc. In my contact surface, we are going to either look for my alloy or type my alloy. And it's right there. You see, this is star, my alloy. It was saved in the alloy manager. It brings the composition we defined, right? Copper, 60% in weight percent. And this is nickel, 40% in weight percent. It did a conversion here probably to mole fraction because we are defining this in moles. Okay, so same idea. So you can go to specs to define non-aqueous lines, show ORP, click OK, and then click calculate. Perfect. So then you go to stability diagram, and here you have it. You have your alloy. And this is the pore bay diagram shading, in this case, the copper system. And then you can switch it to your nickel system in the customize. shade subsystem. And then you see where the region for the passive layer is, where the corrosion region is, etc. Any questions about this? Alloy Manager? Again, this is not an Alloy Manager for corrosion rates. This is exclusively designed for pore bay diagrams, because this is creating a solid solution, and we calculate this solid solution thermodynamics, but it's not for corrosion rates. Okay. So with this, I'm going to stop there and not talk more about pore bay diagrams. There are many more examples I have created in my slides and also in the manual. You can see the effects of what happens when you increase temperatures, pressures, when you are working with alkaline mods when you're drilling, for example. What happens if you don't have water, but you have ethanol or methanol, right? Pore bay diagrams like that, you can create as well. We already covered the Alloy Manager. And these are the highlights. I already talked about them. This is not going to give you a corrosion rate. This is purely thermodynamics. And we are working only on all these pore bay diagrams are doing thermodynamic equilibrium. And